So let's talk about geometric series. A series in general is a potentially infinite sum of numbers or terms. All of the examples I have here are of series. The first two are infinite and the last one is finite. In a geometric series, terms differ from each other by some common ratio. So in the first example here, the ratio is a half. So to arrive at any subsequent term, you multiply the preceding term by a half. So 1 times a half is a half times a half is a quarter times a half is 1/8. To determine the ratio, we just ratio any two consecutive terms. So here we would do 9 over 3, which is 3. And then in the next example, we would do -6 over 3 is -2. So of course, it is important in which order you take the ratio, and it is important to pay attention to any negative signs. Now, if the ratio falls between -1 and 1, or the absolute value of the ratio is strictly less than 1, then the geometric series converge. So that sort of makes sense. If your terms keep getting smaller and smaller, and they're getting smaller and smaller because you're multiplying them by some number that's less than 1, then you expect the series to converge. However, if you're multiplying your terms by some number that's larger than 1, then you can expect the terms to grow really large and the series to shoot off to infinity. Then we have some formulas on how to compute the sum of the series. And here, inside the formula, we use the typical notation for geometric series, where this a is the first term of the series, and then r is, of course, your ratio. And then n is the number of terms. So in the first example, a is 1. In the next example, a is 3, and a is also 3 in the last example, because those are just the first terms. And then the only series that's finite here is the last one, and here we have 6 terms, so n is 6. Then we have the formula for the sum of infinite series, and of course it only makes sense if the ratio in absolute terms is less than 1. So now let's compute the sums of the series that we have here. So in the first example, we're going to use the infinite sum formula. So start from 0 up to infinity, and then a was 1, and r is a half. So a half to the power of I, and then we just plug things into the formula. So a is 1, and then we have 1 minus the ratio of the half in the denominator, and that becomes 1 over 1/2, which is what 1 minus a half is. So the sum is 2. In the second example, the series is infinite, and the ratio is not between -1 and 1. So it makes no sense to try to compute the sum of this series. It diverges off to infinity. So the second example diverges to infinity. In the third example, the ratio is still not between -1 and 1. However, in this case, we're dealing with a finite series, so we can apply the finite series sum formula to figure out the sum. So we just plug things in. So this is going to be the sum from I equals 0 up to 6 minus 1, which is 5. And then a in this case was 3, and r and r was -2. So 3 and -2 to the I. And then we just plug things in onto the right-hand side. So a is 3. And then here we have 1 minus -2 to the 6 over 1 minus -2. And then 2 to the 6 is 64. And negative disappears because we have an even exponent. So this is 1 minus 64, and then 1 minus -2 is 3, so the 3's cancel and we just get -63. And if you just brute force add all of those numbers, you are going to get 63. So let's work through a few more examples that are a bit more involved. In the first example, we are being asked to find an infinite sum of geometric series, and we can read off its ratio to be 2/3. So the ratio is less than 1, so the series is going to converge, and it does make sense to apply the infinite sum formula. However, we cannot apply the formula directly because in the formula the starting index is I equals 0, and in our case the starting index is I equals 5. What we can do is we can say, well, let's just go ahead and compute the entire sum from 0 to infinity, and then we'll just subtract off the first 5 terms that we overshot. And we can even apply the finite sum formula to do that for us. So let's write this out. So we'll do the sum from 0 to infinity of 2/3 to the I. And then we'll subtract off the sum of the first 5 terms. And now let's apply the formulas to compute those. So everywhere here, a is just 1. We're going to apply the infinite sum formula to figure this out. So this is just going to be 1 over 1 minus 2/3, which is our ratio. And then we're going to apply the finite sum formula to figure this out. So this is going to be 1 multiplied by 1 minus 2/3 to the power of 5. And then over 1 minus 2/3. And then we see that we have a common denominator here. So we can apply that. So in the numerator, we're going to get 1 minus 1. And then those two minuses turn into a plus. So this is going to be plus 2/3 to the power of 5. And then we'll have the common denominator of 1 minus 2/3. So then the 1's are going to cancel, and we are just going to get 1/3 in the denominator. And I'll also apply the exponent to the fraction. So we'll get 2 to the 5 over 3 to the 5 all over the 1/3 that's coming from here. So, and then we just divide the fractions. So we're going to get 2 to the 5 over 3 to the 4. And that works out to be 32 over 81. And then you can run this in Wolfram Alpha. Like you can tell Wolfram Alpha, tell me the sum of the series 2/3 to the power of n from 5 to infinity, and it is going to tell you that it's 32 over 81, which is what we got. Okay, so in the next example, we are being asked to find the finite sum of this series, and we have the formula that goes up to n minus 1, but we are being asked to find it up to n plus 1. So you can probably guess that you can just, like if this is shifted by 2, then this is just going to get shifted by 2. And that's exactly correct. So we are going to get something like this here. So we're just going to, instead of n, put n plus 2 here. And then this is going to be 1 over 2/3. And then we won't be able to simplify this all the way because we don't know what n is. But we can just simplify the denominator, which is going to be 3. Well, it's going to be 1/3 if you subtract those, and then you flip the third, and you're going to get 3. And then 1 minus 2/3 to the power of n plus 2. If you wanted to do things a bit more formally, well, you can say, so I'm looking for something like, I'm going to be looking for something that looks like some m minus 1 here. And then I know that the sum from 0 to m minus 1 of 2/3 I, by this formula, by the finite sum formula, is going to be 1 minus 2/3 to the power of m over 1 minus 2/3. So, and then from here, we know that m minus 1 is n plus 1. So to solve this for m happens to be then n plus 2. So then you can just substitute this back in for m, and you get n plus 2, and then over 1 over 2/3. So you get the same answer as we got. This is just sort of a more formal way how to do that. If you sort of wanted to go by the book and just apply this formula directly without having to intuitively guess what this exponent is going to be. In the final question, so here we're once again looking for a finite sum. However, we can't quite apply this directly because we're going here from 0 up to m minus 1. But here we're going from 1 up to n. So we're once again going to have to introduce some sort of an index j, where j is going to be I minus 1. And then we can solve for I to be j plus 1. So then the sum here is going to turn into the sum from j equals 0 up to n minus 1, and then to the 2 over 3 to the j plus 1. So here I'm using this equation that we derived. So, and this is going to be the sum from j equals 0 up to n minus 1 of 2/3, and then 2/3 to the power of j. So then you can apply the finite sum formula with this term here being your a and your ratio still being 2/3. So this would be 2/3 multiplied by 1 over 1 minus 2/3 to the power of n over 1 minus 2/3. So this here is going to be 2/3 1 minus 2/3 to the power of n, and then this is going to be 1/3. So then the 3's are going to cancel, so you would get just 2, and then 1 minus 2/3 to the power of n. So here we shifted the index. We wanted to have I equals 0. We wanted to have some index where it would have been equal to 0 here, so we just needed to subtract 1 from I. By subtracting 1 from I, we also end up subtracting 1 from n. And then that caused this index to shift into j plus 1, which we then took apart using the laws of exponents. And that set a to be 2 over 3, and then the ratio still stayed the same. So we then just applied the finite sum formula.